Newtonian dynamics are the backbone of physics. They look simple, but they have very powerful implications. Since motion and interactions are involved, relativity and energy conservation must also be considered. This video is a dialogue about mechanical laws and dynamics of interactions. Some topics will be simplified and representation will be out of scale to help explanations. Interactions with fields such gravity will be explored in the next video. The first law refers to inertia and conservation of momentum, and is inherited from Galilei. We are floating in our spaceship observing some objects. All these movements will be conserved if nothing interferes with their path. From our reference frame we can define their velocity and quantify the amount of energy as invariant mass. These systems are free and independent. Velocity is not energy that they are actually carrying. So, as example, the total energy of this system is still just its mass. Otherwise, we would run quickly into conservation issues. Since no point of view is preferable, relativity of another frame of reference is equally true. By simple Galilean transformation we see that each object have now different velocities. But no system can actually possess different amount of energy at the same time just because of the observer. So we must use equation 1. The additional energy is not within the systems and depends over the relativity. Thus, conservation of momentum refers to the energy of a mass lacking measurable accelerations. If collision occurs, the theoretical energy from velocity becomes true, with gamma here representing any kind of relativity between the systems. But the first law is not enough anymore. Collisions let us mention the assumptions of conservation. Here satellite and asteroid are on incident paths. Because of the high velocity, with the collision a huge amount of energy seems to appear out of nowhere. In the open universe, very often we can trace back what created this relativity. But no experiment ever violated the laws of conservation, so we must assume that as this collision will respect conservation, so must the cause that led to this relativity. The additional energy from velocity is still in agreement with the principles of conservation, but it can come from remote places and be the result of uncalculable events that ultimately led to this collision. The frame of an external observer doesn't change the univocal reality of interaction. This conservation is between galaxies, but the relativity of the systems involved is the only one that counts. What changes is how and when each observer witnessed the event. All in all, what matters as first law is how each system independently conserves momentum without spontaneous changes thanks to their inertia. Here there is no absolute motion because of their equivalence. What we observe from our relativity is as good as any other frame of reference. And despite most of the times Galilean transformations are enough, with the high relativity gap up to the speed of light, we must use Lorentz transformation. While the first law is about the state of each system, the second Newtonian law refers to interactions. We live in a causal universe, so first thing is to identify the role of each term in this equation. F is the cause and must have an external origin, while A is the effect and M is the target of the interaction, and it's a different system from the one expressing the force. A system accelerated by a force is not conserving its momentum, finding itself in contrast to first law. Many causes can alter the state of motion of a system.
Yeah, fits.
Let's see how Kenny Blankenship does with the boulder dip. Looks like you've got good mobility.
A force can be expressed with different types of interaction.
There you are. Now.
and most of the time we have to transform energy from chemical reactions to mechanical interactions with push or pull. Light too has force. Particles can receive radiating energy and accelerate. Lasers can be used to manipulate microscopic objects. And light can also propel crafts equipped with solar sails. Here we use equal amount of energy to accelerate three systems. The same force will cause more acceleration and speed on the lighter system, half the mass, double the velocity. And the two will end having different displacements, but conserving the same momentum. A certain amount of energy, even used over different amounts of time, leads to identical final momenta. And on B and C we did the same work with different power. Overall, a certain amount of force gives one specific momentum, while work and velocity are mass dependent. Until now we intentionally applied a force to change a state of motion, but inertial mass can also be considered an endless source of reactive force, as we will see with Newton's third law. Within collisions, incident systems accelerate. This emerging force is not coming from the outside, but from the relativity of interaction acting against the inertia of first law. In any case, the consequence of a net force is a system possessing more energy because of a velocity in that same direction. This is kinetic energy. Kinetic energy is quantified with the change in velocity of a mass because of a force of acceleration, both for positive and negative values. When we deal with complex systems with multiple forces and interactions, it is easier to consider kinetic energy and potential energy in place of Newton's vectors. The simplest oscillators are typical for showing this. In ideal condition, the applied force is conserved without energy loss, alternating max kinetic energy and max potential energy. Compared to Newton, these two terms are differently combined. We have effect of mass and cause on the same side, and B reaches the highest kinetic energy while a small cause is acting on it. It derives from different approaches to the problem. The time evolution must respect conservation of energy as a whole. The effect accumulates while the cause runs out, and vice versa. On the other hand, with Newton we have a cause-effect relation for each instant. So for the higher acceleration we need the highest force. What we want to consider here is the aleatory nature of kinetic energy. A certain amount of energy can only generate one state of motion regardless of the mass. Kinetic energy is instead 1/2 mv squared, and since a smaller system will inevitably be faster, we can conserve energy with a wide range of works and kinetic energies. These two are equal, but they refer to different works and energies, because conservation is about momentum. So kinetic energy is the quality for a specific momentum. Kinetic energy can strongly depend on relativity, but it always relates to interaction with forces and both positive or negative changes in velocity. In general, a system conserving its momentum as first law has no kinetic energy. With the accelerometer we can define two distinct states for a system. One is conserved with just the invariant mass. It follows Newton's first law, and the overall energy is just equation 1. And the second state with acceleration and kinetic energy because of a force against conservation. Here there are interactions and relativities, and we use energy.
It's so quick, it can destroy your entire face.
When the force stops, the system returns to its state of rest with no additional energy, whatever speed it gains and whatever energy we spend. What remains always true is that accelerated state is not conserved. Accelerating a system by means of a force leads us to an important effect we haven't faced yet, and is described by the third law. Before the interaction, the two systems are independently conserving their momentum, following the first law. As I try to move the sphere, I will inevitably receive an equal opposite force from the target. Conservation of momentum of the first law can thus be extended to interactions with the third law. This is F equals ma, but the force I put in also comes back as reaction. With the interaction we have twice the second law, and we conserve one momentum accelerating two systems. After the interaction, the overall momentum is the same, 0 in this case, but thanks to a force, we changed how it's conserved, and this 0 comes now from two independent momenta. When I push, it pushes, when I pull, it pulls with a mirrored force. For the effect it is fundamental to possess inertia, but the reactive force doesn't depend over the mass of the system. It depends on the force expressed on that mass. Invariant mass quantifies the velocity in the momentum. Since I put the same force in both cases, I accelerate the same regardless of the mass I'm pushing. On the other half, two different inertia will result in two different accelerations and velocities, but still the same momentum. On Earth, the symmetry of third law can be overlooked because of gravity and friction. When we push something, we use additional forces to deflect the reactions toward the ground. So it looks like only one acceleration is occurring, but it's not. On this side there are even more forces, and it is only the net result, accelerating the Earth, that allows for stationarity. Because we can only move conserving the same amount in the opposite direction. The third law is everywhere. The sphere hits the plane with force that accelerates. So a symmetric force is on the sphere, but velocity will be here much greater because of the lower mass. In the ideal collision, the sphere will reach back the same height, while here the sphere gradually disperses its potential according to the elasticity of the interaction. This is very elastic. This is quite inelastic. Everywhere a force is changing the state of motion, the target is reacting following the third law. For as much force the locomotive expresses on the car reacts on the locomotive, so they both act to pull on each other. The locomotive is heavier, so the car moves more. From here, the interaction propagates, repeating the same behavior. Action-reaction effect is exploited to fly. Wings squeezing down air get lift as reaction. Or propulsion of rockets and airplanes, where the force of the engine pushes gas in one direction, getting opposite thrust. In these complex environments, there can be forces without accelerations. The airplane is dissipating energy because of drag. So the engine keeps exerting force just to maintain constant velocity. Until lift kicks. So, acknowledge the presence of forces just by means of observation is not always trivial. There can be forces without speed. While inside an airplane we infer forces, but we can stand as on the ground. And jumping out we have downward motion, but no force.
It's been every kid's dream to be in a Hot Wheels car, and here at X Games we're gonna do it big time in a few moments.
The third law is usually considered between systems sharing the same frame of reference. But we'll see here how conservation of momentum can also exert force. The initial condition has velocity, and gravity is not fundamental, but weight will contribute to this result. The car conserving a relative speed wants to keep going straight, while the ramp begs to something different. The car expresses force to conserve its linear momentum, so it accelerates the ramp. The ramp reacts with an equal opposite force, affecting the momentum of the car. Without gravity, the two could easily bounce away in a collision-like behavior.
This is the view from Great Tracy.
Weight sticks the car to the ground strongly enough for the loop. The car has now angular velocity, because it wants to conserve linear momentum and is constantly deflected by the reactive force of the ramp. Car and driver don't feel their own action against the floor, but it can be measured the symmetric reaction of the ramp. This is the centripetal force that is pushing the car, while the driver feels apparently centrifugal because the ramp is negating part of its conservation. Centripetal force is reactive and depends over the force we put in, combining conservation of momentum with radius. So, as example, increasing the velocity of the car without changing radius, we increase the magnitude of conservation and so the symmetric push of the ramp. When we remove the interaction, both forces and rotation are disappearing, and the result is the tangential velocity as the only momentum the system was carrying and can conserve. The same is true with a rope holding a rotating mass. The object feels the centripetal force of the thrower, while the athlete feels conservation of momentum of the hammer. This is the true centrifugal force, while on the weight there is apparent centrifuge. When the interaction stops, the two forces disappear and both systems keep conserving their linear momentum. So, until the car has enough velocity and doesn't move the ramp, it will stick to the loop.
And they've done it! And here we go for the jump! And Greg Tracy lands first and
Angular momentum can be conserved if you have at least one force keeping all together without losing energy in the process. But inertia doesn't spontaneously conserve angular momentum. Putting all together, Newtonian mechanics can be summarized with this symmetry. The first law refers to inertia of each system and how they keep their state of motion regardless of the relativity. This is the point of reference, a free independent system conserving its momentum. The second law shows that apply some force to a system will cause it to accelerate against conservation of momentum. F equals ma is the cause-effect relation, but it's only half the story. With every action comes the equal opposite reaction, so each of these interactions is 2 mirrored if equals ma. We can end up adding the relativity between frames to account for velocity, but also to make clear that the third law conserves the overall momentum between different systems. So the forces of interaction do not cancel out, and they appear on different systems. We use it for the second law, but this is how our ideal oscillator appears to respect conservations. The force of the spring is symmetric. Here we have most of inertia on A, so that most of velocity is in B. But if we change the ratio of inertia between the two systems, acceleration too changes distribution. Here in all cases we have the same force and momentum, and just the ratio between masses is changing. Since energy is not dissipated, momentum is internally conserved, and the overall swing will bring nowhere the oscillator. Every Newtonian interaction has the symmetric effect of the third law. Acceleration will appear in both systems, but the magnitude depends on each one's inertia and a lot of additional factors. If you enjoyed the ride, hit those buttons and also consider the series on what is wrong with quantum mechanics.
Hello?